section 1.7, we're learning about counting techniques. And it turns out I've actually taught this to people in pre-algebra before you, so you've probably done it in some math class, so it might seem familiar. Okay, and if not, it's always a good review, or something new to learn. So we have counting techniques. First we'll learn about the multiplication rule, or the fundamental counting principle. So this says, it sounds very official, it's not as bad as it sounds. If you have an experiment with k components, for which the number of possible outcomes are n1 up to nk, then the total number of experimental outcomes would be n1 times n2 times n3 up to n4. Okay, so again, let's just look at what this actually does. If Jill has 4 pairs of slacks, 5 dress shirts, 2 pairs of shoes, and 3 jackets, that means there are 4 different things that she's kind of putting together, or 4 components. Okay, how many possible outcomes does she have? Okay, well, you would just say, okay, well, first she has to pick a pair of slacks, and she has 4 slacks to choose from. Then she needs a shirt. She has 5 shirts to choose from. She needs shoes, but she has 2 shoes to choose from. And she needs a jacket, and there are 3 jackets to choose from. So you just multiply all of those choices out, or she would have 120 different possible outcomes, or outfits. And to do this, if a long time ago you might have started off and you could have done a tree diagram and you said, okay, she had 4 shirts, and then from each shirt she had 5 pants, and then from each pant she had 2 shirts, and when you're done you count up your total possibilities, but that's going to take a really long time because there are 120 different combinations, or possibilities. I shouldn't say combination because that's going to be an official word later on. Okay. A store has 3 types of DVD players, 23 types of televisions, and 7 types of speakers. How many possible ways can a customer select a home entertainment system with a DVD player, TV, and speakers? Well, you say, okay, first I need DVD, so that's 3 options. Then I need a TV, that's 23 options. And then I need speakers, and there are 7 options. So if you put all those together, you have 483 different sets of options. Then we can draw items with replacement. Okay. So let's say we need to choose a 4-digit PIN, say for an ATM. You can choose any digits from 0 to 9 with replacement. So that means you can reuse the number again. How many possible pins are there? Okay, so for my first number, I would have 10 options. For my second number, I can reuse it, so I would still have 10 options. My next one would be 10 options, and my next one would still be 10 options, so 10 to the power of 4, or 10,000. Now, we have an actual formula here. So if you want to draw k objects from a pool of n objects with replacement, then there are n to the k possible ways to draw the objects. I usually don't try to memorize these formulas. I usually try and do it out like we did up above, because in our case, this was, we needed to draw 4 numbers, and we had 10 numbers to choose from, so we did 10 to the power of 4. Now drawing items without replacement, so we need to get a 4-digit PIN again, but we can choose any numbers without replacement, so that means you can't use the same number twice. So how many possible pins would there be? Well, the first time I have 10 numbers to choose from. The second time I will only have 9 numbers to choose from because I've already picked a number, and then I'll only have 8, and then I'll only have 7. So this is only 5,040, so that cuts down quite a few options, doesn't it? And so for this formula, if you want to draw k objects from a total pool of n objects without replacement, then there will be n times n minus 1 times n minus 2 times n minus 3 up to n minus k plus 1 possible ways to draw the objects. So again, this is much more complicated to me than just thinking it out. But in our case, we wanted to draw k objects. So we needed k objects, and we had a total of 10 numbers to choose from, but it's without replacement. So we would need to do a 10 times, and then you subtract 1, and then you subtract 1, and then you subtract 1. So the 7, if you think about 10 minus 4 is 6, plus 1 is 7, and that's where you stop. To me, it's easier to do out 4 numbers and stop after I've written 4 numbers. Okay, factorials. Factorial is a special symbol, so n with this exclamation point. We call that n factorial, and we define n factorial to be n times n minus 1 times n minus 2 all the way down till you get to 1. And just as a side note, 0 factorial is defined as 1. So in our case, if we wanted to say, well, let's say, what's 6 factorial? That would be 6 times 5 times 4 times 3 times 2 times 1. Usually there's a factorial button somewhere on your calculator. If you don't know where it is, go to Google, type in your calculator, factorial, and something should come up. So we have what's called a permutation. So we use a permutation when we want to select k objects from n objects, and we're selecting the objects without replacement, and the order matters. Okay, so the key thing here is order matters. The number of possible permutations of k objects from n objects is, and you have special symbols, and each class writes these symbols slightly differently. We'll do a p with an n and a k, and the way you'll do this is you'll do n factorial all over n minus k factorial. So first, we want to show that this formula is equal to our previous formula we wrote down of n times n minus 1 times n minus 2, etc. So that was up here. We wanted to choose a pin, and we can choose any. We want to pick 4 numbers, and it's without replacement. So factorial, we said without replacement. And if you're talking about a pin, would the order matter? Yes, of course. We want to keep things in the same order. So that is a factorial. So let's look at our actual formula. So p n k. So we're going to do n factorial over n minus k factorial. So let's see what that would be. N factorial, you start when you write n times n minus 1 times n minus 2 times n minus 3 dot 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 until you get to n minus k plus 1, and I'm going to make sure I have that one in there because that's what I'm trying to get to, and n minus k and n minus k minus 1 dot 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 all the way down to 1. So each time I just subtract 1 and get 1 less. And n minus k factorial would be n minus k, and then you subtract 1, so n minus k minus 1, n minus k minus 2 dot 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 down to 1. So notice here what happens. N minus k minus 1, those are matching up, right? N minus k minus 1, n minus k minus 1, 1, 1. So basically all of that cancels. And we're just left with n times n minus 1 times n minus 2 times n minus 3 dot 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 down to n minus k plus 1. And so this is kind of a simpler formula, or a formula you could do if you wanted a factorial. But it's usually easier just put the factorial into our calculator than it is to actually multiply this out, especially if you're going to be doing very many, because your calculator does know how to do it. So let's look at this example. 16 tennis players compete in a tournament, and how many ways can the rankings for the best 5 players be assigned? So this makes sense that order would matter, right? Because first is different from second place, is different from third place, okay? And it'd be without replacement because the same person can't be first and second and third and fourth. And in this case, we have 16 total. We want to draw 5 of them. So we're looking for the permutation for 16 total, and we want to draw 5. So the formula says you want to do n factorial, or 16 factorial, over n minus k factorial. So that's 16 minus 5 factorial. So my calculator, I could put in 16 factorial over 11 factorial. Or usually I can just put in this thing right here because there's usually a permutation button somewhere on your calculator. If there's not, there will at least be a factorial button. So 524 160. If you actually wanted to write it out, you could. It's still small. If you could put in your calculator, although your calculator might give you an error because you're going to get really big numbers. 16 times 15 times 14 times 13 times 12 times 11 times 10 times 9 times dot 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 down to 1. And over 11 factorial, so 11 times 10 times 9 times 8 dot 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 down to 1. So notice these would cancel, and you'd only have to do 16 times 15 times 14 times 13 times 12. So that's a permutation when order matters. A combination is the exact same thing, but the order does not matter. And this formula is slightly different. Notice we'll be dividing by a bigger number, so we put in this k factorial on the bottom. The reason why is if order doesn't matter, you will have less options in the end. Okay. So you write c and k, or we can also use this nice little symbol, and this is called n choose k, or sometimes it's called like the binomial coefficient, but we'll usually say it's n choose k. And this one is even more likely to be in your calculator somewhere, but you'll do n factorial over n minus k factorial times k factorial. Suppose we want to draw a hand of 4 cards. The order you draw the hand in doesn't matter. And this makes sense in a lot of games. You just draw 4 cards, hold them in your hand, and all 4 cards are just kind of in this similar pool. You can reorder it, it doesn't matter. How many possible combinations are there? So we want to draw a hand of 4 cards, so there would be 52 cards total. We want to draw 4 of them. So we are looking for C of the 52 4, or we're looking for 52 choose 4. So at this point, you could just put it in your calculator if you have that button, or you can say, okay, it's n factorial, so 52 factorial, over n minus k, so 52 minus 4 factorial times k factorial, or 4 factorial. And this is 270,725. So that's a lot of different combinations of 4 card hands that you can get. The hardest part, of course, is mixing up the scenario and trying combinations and permutations together. So find the number of possible choices for each scenario. Let's see. A garage employs 7 mechanics. 3 are needed on one particular job. And how many ways can the assignment be made? So if you look at this, would the order matter, yes or no? Okay, so you need 3 people on one job. It probably doesn't matter whose names you call off first. So I would say order does not matter. And when your order doesn't matter, that means it is a combination. So we'll do a combination. There's 7 total. You want to choose 3 of them. So n equals 7, k equals 3. Let's write down our formulas. For a combination of n choose k, this is n factorial over n minus k factorial times k factorial. So this will be 7 factorial over 7 minus 3 factorial times 3 factorial is 35. If you wanted, you could have also written this was 7 choose 3 is 35. In our next one, at a rural high school, class officers are selected from a senior class of 50 students. How many different ways could a president, vice president, secretary, and treasurer be chosen? Now in this one, order does matter, okay, because being president and treasurer is different. So the first one is president. That would be different from someone else being the treasurer. So order matters. So this would be a permutation. We have 50 total. We want to choose 1, 2, 3, 4 of them. And a permutation is n factorial over n minus k factorial. So this would be 50 factorial over 50 minus 4 factorial. Or 5,527,200. So that's a lot of different ways that you could choose your 4 officers. Let's see. How many ways can 4 students from a group of 15 be lined up for a photograph? So if we're lining them up, I would think that the order would matter here. So this would be an order one. So a permutation. There are 15 total out of 4. And at this point, I'd probably just start putting in my calculator. Is 32,760. Now in my calculator, you might see things that look like P and K, or I actually have a NPR, or maybe it would be an N, P, K. So mine uses an R instead of a K. Those are some of the symbols that you might look for as you're trying to find it on your calculator. Okay, let's see. Suppose the senior class is governed by a committee of 4 officers of equal rank. So that sounds like you don't have positions. You're all just kind of thrown in there. So how many ways can the committee be chosen? So that sounds like no order. Because they're equal rank, it doesn't matter who's in which position. Let's see. So we want to choose 4 people. I don't know why these are all choose 4. Oh, and our senior class is governed. Let's see. We don't actually tell you how many people are in our senior class. I think I mixed up number 3 and 4. So I think we're still supposed to have 50 students. So let's do a combination of 50, choose 4, or we could write it as 50, choose 4 if you prefer. So 50, choose 4 is 230,300. So I should put 2 and 4 back together again. If the order matters, there was over 5 million ways to choose. If the order doesn't matter, there's only 230,000. So that makes a big difference. And finally, number 5, John is working on his magic tricks. He pulls a card out of the standard 52 card deck, looks at it, and puts it back. He does this 6 times. How many possible sequences of cards are available? Now that word sequences makes me think that the actual order would make a difference. Okay. But actually, let's pay attention here. Notice he looks at it and he puts it back. That means it is with replacement. Now, permutations and combinations are never with replacement. Okay? Because like when you're looking at a senior class, it doesn't make sense to choose the same person over and over because you just have 1 person instead of 4 people. So if it's with replacement, it can't be a permutation or combination. So it can't be a permutation or combination. So you have to pay attention. We kind of got going in our groove, and this one throws us off. Okay, so you could go back to your other formulas you memorized. So with replacement, drawing objects with replacement, that's just n to the power k. That was the only one we learned about with replacement. Or I probably would have just thought about this one and I would have just said, okay, there's 52 cards. The first time he draws a card, he has 52. The next time he draws a card, he has 52. The next time, 52, 52, 52, 2, 3, 4, 5. And his 6th card, he still has 52 choices. So this was 52 to the power of 6. Or n to the power of k. So we've done all these different ways to count. The whole reason you count, at least in this class, is so then we can find probability. Okay. So let's go through. Here, let's see. Suppose 9 out of 500 chips in a box are defective, and 3 chips are sampled at random from the box without replacement. What's the total number of possible samples? Okay. Let's see. It's without replacement, so that means it could be a permutation or combination. And do you think that the order matters which chip I draw first? I wouldn't think so. We're just drawing out 3 chips and looking at them, so order does not matter. Okay, so we want to know what's our total number of possible samples. So this would be a combination. We have 500 to choose from, and we want to draw out 3 of them. So this would be 20,708,000. Oh, 708,500. And we want to know what's the probability of choosing 3 defective chips. Okay. So first, how would we have done this problem before this section? So these permutations and combinations, it's kind of just one different way to do all the same probability problems we've been doing. We could have done this before, and to me, this is actually a little bit easier to do it, what we would have done before. You would have said, okay, I want to choose 3 defective chips. So I need a defective, and then a defective, and then another defective. And I said, okay, if I want to draw a defective chip, there's 9 out of 500 that are defective. So my first defective chip would have been 9 out of 500. Then I need to get another one. But I'm not going to put the chip back each time. So if I want another defective chip, there would only be 8 defectives out of a total of, I already took one out, so 499. Then I need one more defective, so it would be 7 out of 498. So each time I have one less defective chip, one less total. And this would have given me 4.05 times 10 to the negative 6. Now, we can also use combinations to find this. I'd say, okay, I want to find a probability. So on the top, we put, let's see, number of total samples. And number of, let's see, we want to get 3 defective chips. So number of samples of 3 defectives. And remember that we had 9 defective total. Okay. So let's see. So first, if we want to get 3 defective chips, but there's only 9 total, we'd have to do 9 choose 3. That's how many ways we can get 3 defectives. And then on the bottom, the number of total samples, we did that up in number 1. So there were 500 choose 3. So first you have to figure out how many ways can you find 3 defective chips, and then how many total samples were there. And you still get 4.05 times 10 to the negative 6. And our next one, let's see, what is the probability of choosing a sample that has exactly 1 defective chip? So this one you have to think about a little bit harder. Okay. In the bottom, we're still going to put our number of total samples, which is still our 500 choose 3. But then on the top, you only want to get 1 defective chip. So first you say, okay, if I have 9 defectives, I want to get 1 defective. But if I only want 1 defective, then the other 2 must be not defective. So that means 1 defective and 2 not defective. So I need to get 1 defective and 2 that are not. So I need to multiply here. So how many not defective chips are there? If there's 500 chips and 9 are defective, there are, let's see, 500 chips, 9 defective, that means 491 not defective. Okay. So we'd have 491 to choose from, and I need to choose 2 that are not defective. So 1 defective, 2 not defective, all over my total number of possible samples. And this is going to give me 0.0522. If we drew 20 chips instead, what would be the probability of getting a sample with exactly 2 defective chips? Now that does mean that we would have 2 defective and 1 not defective. So we're going to do this very similarly. So first I want to draw 2 defective chips. There are 9 defective to choose from, and I want to draw 2 of them. But then that also means I still need to have 1 that's not defective. So there's 491 not defective, and I only want to choose 1 of them. Now for our number of total samples, there are 500 chips, and this time we want to draw 20 of them. Now it turns out I tried to put this in my calculator, and it wouldn't let me do it. So I went to this website called wolframalpha.com. And I use this a lot. If you have integrals, derivatives, it'll take almost anything. And I tried to figure out, how do I put in that 9 choose 1? And I could just type out parentheses 9 choose 1 times 491 choose 2 over 500 choose 20. And it tells me this is 4.059 times 10 to the negative 30. So that's why my small calculator didn't like it. So because we're asking to get 2 defective chips, there's not very many defective chips in there, and so that probability went way down.